Brace yourself. Want to start? Or
Well,
we can just say how we started approaching it together as a team. We basically wrote down the Euler-Lagrange formula. And then we wrote down the Schrödinger equation, and then we sort of stared at it for a while and just sort of tried to like work backwards, so we know what we're supposed to get and we know how we get there, but we don't know where we start, so we just sort of guessed, and it was a lot of trial and error and a lot of okay, wait, put a minus here, or wait, maybe this should be this, and then you just keep switching things around until you get something that works when you put it in the Lagrange.
This is how it's done in practice too, by the way, so
Okay.
it really is. Trial, error.
We did two different methods as well. One also using the Hamilton-Jacobi equation, which we didn't.
okay.
Understand. Like it.
It's mathematically equivalent to what we use in Euler-Lagrange. So there's no new information there. It's just different version of the same techniques.
Okay. I'm just gonna write it out. Because basically we just were in the lecture hall, like on the board, just writing stuff and erasing stuff over and over again until we got to this and tried it in, so we can just show you what we have.
Yeah, so actually you don't really have to guess fully, like trigonometric equations, but you know from basically this thing is that what your Lagrangian, your derivative, your Lagrangian with respect to q, minus your Lagrangian with respect to q. Basically, this thing equals to 0. So what we actually try is something like this. So the Lagrangian divided by derivative of this q, the q down here. The derivative of equals to some function, and the derivative of the Lagrangian with respect to q equals to 0. And this function would result in basically this Schrödinger's equation. And then we tried that. Apparently, it didn't really work out because what we got is some function with derivative squared. The derivative with respect to, for example, x squared. So that, for example, when you take the derivative of this thing and put psi here, you end up with the derivative of psi by, for example, dx, and then you have another derivative of dx, so that you end up with a d squared over dx squared of psi. So we tried this function. Apparently, this doesn't really work out because when you plug the energy equation, you get this different energy solution. So what we then try is dl equal by dq equals to some function instead, and that turns out to be this Schrödinger's equation. And then when you sort of plug into the energy equation, you get back your Hamiltonian. So that's more or less like 90% trial and error. Apparently, you can go from your Hamiltonian or your energy to the Lagrangian by this, but I'm not sure. Like we do know how to get from this to this. Is just what we did in the lectures. But I'm not sure how to go backwards.
Up there, is it an F or is it another L?
It's not.
No, all the way up in your first equation.
This is an L.
That's an L.
This is the EL.
Yeah, but we're not sure how to get back.
I'm sorry, about the arrow?
Error?
Hey, what was written about the arrow, sorry?
Transform. That's the method we're supposed to use.
Yeah, sorry, I just couldn't read that.
Do you want to show it?
You need to show.
I'm not actually sure how that works, but because
No, not the Lagrange transform, but I need this.
Oh,
Do you want to show that?
well, we got the solution. Well,
Yes, but maybe you can show that this is actually the solution.
Okay. So
Just to be sure, what is psi t?
psi t is just a function psi t which is different from this guy.
Okay, well, what is psi t?
It could, for example, be the time component because we actually need the time component inside.
Oh, I see.
Or we could just have a complex number.
Sure.
A complex number. So for example, if you plug this thing inside, you have dl by dq. That's
Q is sine t, right?
oh yeah. Well,
Well, not have to do that.
So L equals to psi t I 0 plus minus psi t psi. So the first derivative is to psi t. This one will give you I V0 psi. This one will give you this.
Equals 0.
Well, actually, it's equals to this. And basically, there's no first derivative of psi t. So this is actually not the derivative of psi t. So this goes in this case, this one goes to 0. This is not the first derivative. The second derivative goes to 0, and this is not the first derivative. So it goes to 0. So in the end, you get this whole thing, which is technically Schrödinger's equation again, which is equals to 0. And that technically how
So
you get the
it's right. You got back to the Schrödinger equation.
Yeah.
basically. This is
What is psi t?
it's basically any function. It's just something that is different from psi. So you can get complex
I see.
psi.
Okay, so you introduce this other function in order to be able to take a derivative with respect
Yes.
to this thing. So you introduce some random function,
Yeah.
doesn't matter what it is. Does everybody see the technique that they've used?
It's sort of cheated.
No.
Yeah, it's not
Yeah, but Lagrangians is really more an art than it is a science. I should be careful now. I mean, of course it's science because you can try all kinds of stuff on it. But getting a Lagrangian is really an art. It really is the same thing as finding out what F is in Newtonian mechanics, right? I mean, this is an example that I used before, a comparison. When you use Newton's second law, F equals the time derivative of the momentum, and you want to actually solve that for something, Newton did the exact same reverse engineering. He knew that the solution should be ellipses, because he knew Kepler's laws were true, and then to reverse engineer what F should have been in order to get Kepler's laws. And then he found the F that we now all know as Newton's universal law of gravity. That's exactly the same thing that you're doing right now. You know from experiments, say, what the equation is, Schrödinger's equation, and you reverse engineer what the underlying thing is that you need in order to get there, in this case the Lagrangian. It is not different from Newton reverse engineering what the universal law of gravity was. So yes, it is a lot of guesswork, but you are actually guessing at actual nature.
Wait, so the psi t is a random psi, or is it the actual?
It could be complex conjugate, but basically it's just something that is different from this side here.
So like when we put it in, we get the Schrödinger back out.
Yes.
Yeah.
Okay.
It could be any
So
conjugate.
is this the same as proving Schrödinger's equation from basic principles?
No, because
So it is not the complex conjugate.
not necessarily. Is it the same thing as proving Schrödinger's equation from basic principles? The answer is no. You choose your Lagrangian in such a way that Schrödinger's equation comes out. The only thing you've done, it sounds so mediocre if I say it like that, but what we've done now is that we've written something that we already knew into a new mathematical form. We haven't actually proved anything new. The reason that we do this rewriting into new mathematics is because Lagrangians allow you to calculate all kinds of more stuff that your original Schrödinger equation didn't, or it was in there in some way, but you couldn't really get it out. The prime example of this is that once you have a Lagrangian, you can immediately write down what the energy is of that thing, which is much more difficult if you just have your Schrödinger's equation or your something. Well, I know what you're going to say now. Okay. No, okay, we'll see. No, there's a subtlety there that we discussed a little bit before the lecture. I'm going to come back to that in a second, but just as a general statement, the reason that we do this complete rewriting of stuff we already knew into some new mathematical forms is that this new mathematical form allows you to calculate new stuff that's much more difficult to find in the original form. This is why people do Lagrangian mechanics. But yes, it is a whole lot of guessing in there. Not complete guessing though. First of all, you know what comes out. That's one. But secondly, and that is a very important part here, you already know that Lagrange should fulfill a certain number of properties. One of them is it should be a number, as opposed to a spinor or a vector or whatever. So you already know that if you want to make the Lagrangian for, say, the Dirac field or something like that, the Dirac field should be in there, but something, the Dirac field itself is a spinor, so there should be something else in there that makes a spinor into a number. That's one. Second thing is, a Lagrangian always has to be invariant under Lorentz transformations. Otherwise you will have that your laws of physics differ from person to person. One other thing is that the energy maybe I shouldn't make that comment, but I'll try anyway. At the moment that you have your Lagrangian and you calculate what the energy is, then you want this energy to be a positive number, otherwise your Lagrangian is crappy. Yes? So you already have a number of conditions that your Lagrangian should fulfill. So it's guessing, but not complete shot in the dark guessing. You already know its properties. There's one thing more. Hi. There's one thing more. Lagrangians allow you to write down what the energy is, and you know that it's conserved because it's Noether's theorem, but Noether's theorem for energy is only a special case of a more general Noether's theorem that tells you general constants or observables that are constant. Suppose that you know for whatever experimental reason that your theory has this number, it should be a constant. Say your experiment tells you that angular momentum should be a constant. Or maybe you find that abstract things like charge or, I have no idea, let's say baryon numbers should all be constant. Then by Noether's theorem, you know that your Lagrangian should be in such a way that these constants actually come out. So just by taking some experimental facts, you can reverse engineer what your Lagrangian should look like. Is that unique? No. Because Lagrangians are not unique. There's more than one Lagrangian that gives you the same physics back. So if you haven't found the actual exact Lagrangian, don't worry. There's usually a whole plethora of Lagrangians that give you the same physics. So this might be one of the ones, this is not the one that I had, but this might be one of the Lagrangians that actually give you a Schrödinger equation. In fact, you showed it, right? You took this one, you introduced some party function here.
Yeah, exactly.
You put it into your Lagrange equation and you actually got the Schrödinger equation back. So that works. This Lagrangian that you have actually gives you Schrödinger's equation. So I mean, there's some good news there. He did some reverse engineering. But this is not your comment yet. Yours will come at some point. Now, he made a very good comment before the lecture. You did introduce another field, right? You introduced some other function. Why did you introduce other function? So you could take derivatives. Okay, but now this means that your Lagrangian now doesn't describe just one field, your Schrödinger field psi. It also describes a second field, psi t. I got an email. So you now Lagrangian describes two fields. But that means that you will have two laws of physics coming out. One for your psi, that's the Schrödinger equation. You construct it in such a way, but you also get a equation for psi t. And you really do want the psi t, that equation of psi t, also to resemble something that is in physics. You cannot just introduce fields and have them obey some equations. So maybe what we should do is find out what the psi t field, what equation that fulfills. And see if that actually corresponds to nature. If not, then this psi t, you were not allowed to just plug that in there. Right?
Yeah.
Key concept, you have introduced another field now. This other field also obeys an equation. And if that equation doesn't agree with nature, then you are not allowed to introduce it in this manner. But maybe it does. So maybe we should just do Euler-Lagrange again, and now find the equation for the other field, the new field, the party field.
Sorry, I have a question just going back basically to the beginning.
Okay.
Okay, you said that you guessed this Lagrangian based on guesswork, and you introduced the psi t to satisfy the differential, but how did you get the stuff within it? The I d0?
This is Schrödinger.
This is, yeah. This is
Schrödinger's
equation.
This is Schrödinger's equation. It's I h bar ddt plus.
Oh, okay, yeah.
We just knew that this had to be in there, so we just thought we would include it because otherwise it would be too hard to derive it from something else.
It is pretty smart though, right? I mean, at the moment that you take this thing and you take the derivative with respect to psi t, so you get just, this is a constant So you just get Schrödinger's equation back. No, it works.
Yeah,
But again,
sure.
my point
You know what it
is,
should look like.
If it works, it's not stupid, but
no, but you're only halfway there. You've introduced a new field, psi t, and this psi t also has its own equation.
yeah.
And well, we'll just have to see if the psi t obeys an equation that is actually agreeing with nature. If not, then your Lagrangian only works half for one of the two fields. So let's see. Let's write down using your Lagrangian what the equation is for the field psi t. And you know how to do that because you have the Euler Lagrange equation.
Yeah.
We basically just did this kind of stuff.
Psi t. Oh,
We did it for some, yeah. So it's the same, so it's there and then it's not.
Yeah.
Not really.
Why?
So suppose that you have here. So this one
Yeah.
will be 0. 0. 0. No.
No, no, it's not multiplied, yeah.
Because there, this will be 0 minus b psi. Yeah, t. And then this one with respect to,
You don't.
let's say, yeah, psi dot. That would be psi t I. Yeah, t. Oh, actually, t0. Which is going to give you I psi dot t. I think I tried this. It doesn't, because this thing goes to 0.
DQ.
It's
Feel free to comment.
x, y, z, du, but then because this is
Yeah.
second derivative, this equals to 0. I think.
Just one question, like why is the derivative, the first two are 0 there, no?
Yeah.
Can I see why?
Yes.
So, basically we're doing derivative with psi.
Mhm.
And so basically what we do is times it here. So what we have is psi t times I times the time derivative of psi.
Mhm.
And in this case what you have is derivative
Mhm.
of psi, and basically you can just take psi t out, I, and you have psi dot, and this is not.
Yeah.
This will
So
be
every time it's say dot dot,
yeah.
Okay,
You sort of
okay.
count it as different variables.
so there is no dot dot, just one dot.
Yeah.
Okay, no, that's good to know, thank you very
That's 0, this will be
Mhm.
0, and I think this should also give you 0, since you don't have a first derivative.
Okay, so what does the Euler Lagrange tell you?
That doesn't work.
The Euler Lagrange tells you that this one derivative should be equal to the other derivative, so you get an equation out.
So you have I psi t equals which you are missing the kind of thing.
Well, why is there something missing? What is
This one with respect to psi t, this is basically derivative with respect to the first
Yes.
derivative of x, y, z.
Okay.
And you don't have the first derivative, you have the second derivative because this
I
is.
agree. But this is what you get out, yes? The Euler Lagrange tells you this is true. That's interesting. I think it's an equation you can actually solve. Time derivative of this thing gives you back the same thing times a function. I mean, that sounds like something we should be able to solve.
Okay.
It says the time derivative of a function equals minus itself times v.
So it's e to the power of some
Oh.
t, I think, minus.
Yeah,
I.
all on one side.
Psi t v. So psi t is equals to e to the power of I.
A 1 over I, no? And then you move it over from the left hand side to the right side. You divide it.
Yeah, but you can cancel 1 over I with, that's the same thing as multiplying by minus I. That's what they did.
Okay.
Yeah, exactly.
Ah, yeah.
I don't think it was derivative, you get
Yes.
back that should be.
Okay, so that's nice. You introduce this new function in order to get the psi to come out right. But then it forces you to look at what this psi t does. Apparently it does this. And this is a function of x or something like that. And this is all real, so what you introduce now is a function that oscillates. Because this equals cosine vt plus I sine vt. So it's a complex function that oscillates in time and in space, because v depends on x, depending on how your potential energy depends on x. It's this multi-oscillatory thing with a real and imaginary part. Oh, okay. Yeah, but it doesn't change the conclusion, right? I mean, it just introduces another minus somewhere, so maybe this. I mean, the solution is still the same. It's going to be some sine of t, cosine of t, some oscillatory thing. Okay, so mathematically you found something, but I have no idea what that is physically. Well, it sort of looks like a wave, right? Okay, suppose that we accept this. Well, maybe there's some unknown function psi t that really works like this, and it was allowed to introduce that thing, to introduce that new field. Then the second part of the question is, given that you have a Lagrangian now, can you calculate what the corresponding energy is? You have a Lagrangian. And if you have a Lagrangian, Newton's theorem tells you exactly what the energy is.
I think those are really so we did was basically put it in those.
Okay, but we can do it now.
Yeah.
Just see what happens.
Sorry, I have another basic question. With the Lagrangian,
It's just the same.
in the Lagrangian is dependent on Q and Q dot, but in introducing the psi t, isn't that unincluded by the Lagrangian itself? You're introducing a new generalized coordinate.
Yes, that's true. So that means for every generalized coordinate you have a new Lagrange equation.
Yeah.
And that's what we're doing now, because they've used their first Q, the psi, to get one order Lagrange equation, to get one law of physics out. That's a Schrödinger equation.
Yeah.
But because you introduced another one, we have to write down the order Lagrange equation, just like you suggest, but now for the new Q. And that gave them another equation, that's that one,
Yeah.
that I don't know how to put into physics.
Okay.
So your comment is exactly my objection to their Lagrange.
Okay. So
Oh, that's fierce, it's good.
Has to be action. So why would stand there with equal energy? Seven, correct.
We basically put in here. And we see that these two parts cancel out as it did in when we did, I think, all the Dirac equation, maybe the Klein-Gordon one. And you're basically left with the But then here we were a bit confused because we were wondering, this kind of looks like the Hamiltonian. Except it should be minus and plus. But then that's also what I was telling you earlier was that if we make
That's what is the moment? This is going to be negative to the moment.
Anna,
we
can
see
you read
what-
this slide? Thanks. Yeah.
It's like this. So from this one, you get basically E equals to minus P, that means P plus B. So you go to that, you get E minus P squared minus B equals 0, and then P squared is, this is nothing minus of H bar, but I'm gonna H bar. So it's plus, so that should be correct. And basically this, and yeah, yes, it's positive, but then you can look back at the moment of pairs where it's gonna be negative, which is negative Hamiltonian.
Which is okay.
So we interpret the result, because you did find something now from Newton's theorem. It's an energy apparently.
Seems to be energy, but
Well, according to Newton's theorem it is. And it should be constant in time, if your Lagrangian does not depend on t. Explicitly depend on
That's
t.
very explicit.
And it doesn't. So by just mathematical fact, Your energy that you've written down now should be indeed a constant of time.
Just change convention.
Yeah, that's what I did in the beginning.
Oh yeah, change convention.
That's what
Yeah,
I
it's a-
said. That's what I said.
Trust me, you cannot just get minus signs in and out just by changing convention. Or sometimes it works because, well, sometimes it doesn't. But yeah. Okay, you have an energy now. Is it constant? Is it positive? By the way, notice here does not tell you guarantee that it's a positive number. It just tells you that it's constant.
Yeah.
Well, actually, no. If you multiply this thing with this negative and this positive, which turns into positive.
Everything. But there's no explicit T part.
And then
Where is it?
Well, this should be negative. Well,
yeah, I mean it's
Yeah.
negative, but then you convert the negative derivative squared to
P squared.
Yeah.
positive.
So then it's all positive.
Okay. Look at that. You did find that the energy is kinetic energy squared plus potential energy squared. And it's plus. So is that correct? From classical physics, you would expect something like this, yes?
Yeah.
So, yeah. I find some good results here. They found the Lagrangian. They did the math, right? I mean, they reverse engineers. The thing is such a clever, by the way. I mean, it's this. I mean this as a compliment,
Okay.
but it really is the easiest way that you could have done this. That is a compliment.
Okay.
So you took that at face value. You had to introduce this new field. I call it party field, but sure. This happy circumstance field. Okay, let's go with it. We took this thing, put it in the Noether's theorem, and we got something out that indeed resembles energy. Potential energy plus kinetic energy, something like that. And then Noether's theorem guarantees you that this should be a positive function. Okay, so I think this is how far you get with this. But here's again, so I'm happy. This is good. I mean, you've used the technique. And you got some results out that seem at face value to be very physical. Drawbacks, anyone? One I already mentioned.
That thing.
Well, I have two fields.
Yeah,
Yes,
two fields.
there's two
So it
fields.
makes it easier.
There is two fields. You have to introduce another field. Well, maybe it's a problem, but maybe this new field that you introduced, the party field, is actually an existing field. Agrees with nature. And maybe it isn't. Given I mean, this is again physics, yes? You just by reverse engineering, you got this thing out. You had to introduce, in your particular case, you introduced this thing. You took that thing, saw that it agreed with this, and maybe then you can now tell the experimenters, well, go look for the party field, see if it exists. From a mathematical point of view, it seems all correct. That you've done all the work and that you got a good result out. Now, let's see if we can do a little bit better. Can we also write down let me rephrase the question. Suppose that we want to describe the Schrödinger field and just the Schrödinger field. What could we have done then to get this out? So no introduction of any new field. You're allowed to if experiment tells you that this new field exists. Suppose that we have no reason to think that this new field exists. So we're not allowed to use this one here. Suggestions. Again, it's more an art than a science, guessing Lagrangians. So what could we use if it's not psi itself? Party field itself. What are ingredients that we have? Sorry?
The conjugate.
The complex conjugate of your Schrödinger field, because you know that that one does exist. If you have a Schrödinger field, you also have a complex conjugate of the field.
Go ahead. Oh, there's only one that works. That's what
Alright, so let's take party fields to be just Schrödinger field, complex conjugate.
Yeah.
Because now we haven't introduced any new fields, we just used our old field and use that as a thing with respect we're going to take Yes, exactly. Now go through the math again. Don't do all the calculations, we already did them. We now have for party field, we have Schrödinger's complex field. We haven't introduced any new thing. Question. What equation does Schrödinger's complex conjugate field now obey? We already wrote it down before. Before we had psi t, random field, and we wrote down what equation it obeyed. It was over here-ish somewhere. We actually solved that equation too. E to the power something.
Minus IDT.
Yes, that was it. Okay. There you go. Yes. No, it wasn't E. It was V. Yes. Okay, there we go. Okay, so we're trying to improve on their solution. We're not introducing a new field, we're just going to take our old field, so it really just explains one field, Schrödinger field. But Euler-Lagrange tells us then we get a Schrödinger equation back, so that's good. We also get now an equation for the complex conjugate of the Schrödinger field. We did that before, that is this. Comments? Is it correct? I mean, mathematically it's correct, but is it physically correct? Thank you. We've actually solved the equation for psi star. It gave us this thing. But that means that we also immediately know what psi itself should have been. It's just the same thing with complex conjugate I. Now, is this a general solution to the Schrödinger equation? We have two fields now. One field obeys the Schrödinger equation, obeys, where is it? This thing here. And one field is always given by that number, and they should be each other's complex conjugates. Is that the case?
Do you need to normalize it, or?
That's not the issue. Ultimately, you have to normalize them, of course. But that's okay. Schrödinger equation is a linear differential equation. You also put some number in front. So once you have the solution, you can also put a normalization in front. And from a physical point of view, it has to be there at some point because it has to be normalized to 1 as such. But that is not the key issue here. Can I write down my question a little bit more suggestively? Two equations, or two fields now. One field, one of the two, is a solution to 2n plus v psi equals I h bar. Okay, not h bars. That thing. One field we have seen, or they've reverse engineered, one field to be the solution to this equation, the Schrödinger equation. That was the starting point. They had to introduce another field. And this other field obeys some equation. We already raised it, but we could actually solve that equation too, and we found the other field is always given by this number, this function. Two fields, and they should be connected because this field should be the complex conjugate of that field. Is that the case? Should it? The question is more mathematics than it is physics.
No, in the first case, psi, the solution of psi can be anything depending on what your potential is.
Yes.
But in the second case, it gives you a very specific solution.
Yes. The solution to this one, the Schrödinger equation, well, you've seen it. I mean, it could be a transmission coefficient, right? In case of alpha tunneling. It could be particle in box, this gives you sines, cosines. It could be radial wave equation spherical harmonics in case of a hydrogen atom. The solutions to this one come in many varieties, depending on how you've chosen this. So it could be For one particular case, it's spherical harmonics. For one particular case, it's a particle in a box. For one particular case, it's a decaying exponential. And what we have now is that all of these plethora of solutions all should be writable if you take the complex conjugate as this thing. I highly doubt that is the case. If you want to be extremely sure about that, we can also do it like this. We take this thing, we take this complex conjugate, we get this. Yeah? If we are to believe that this is true, that psi star is this, that psi itself is that thing, and that should always be a solution to this differential equation. Now put this thing back in here and see if it works. I'm highly doubtful that it does. For all random functions v of x. Well, if you go through the math, trust me, this probably won't work. Yes.
So this only works for a non-uniform field?
By non-uniform, you mean?
Like the potential is, it won't be constant.
If it won't be a constant.
Yeah, because otherwise you can't differentiate the wave function according to delta squared, right?
That's true. Then the derivative of this one with respect to x, y, and z would just be 0 for a uniform field. And then this contribution would be 0. And hey, then it actually works. You see that? Their solution does work at the moment that your v is a constant. If v is not a constant, then, well, you can just plug it in and see that it doesn't work generally. Unless maybe for some very special cases of v. But generally, for v not a constant, this solution and this solution are not compatible. So what does it tell you about the Lagrangian that you started out with? It gives you two solutions and they're not compatible. It gives you two pieces of physics. And
it's not physical.
It's not physical. It doesn't work. It works from a mathematical point of view. It does give you the Schrödinger equation. It does even give positive energy. That it gives you not a positive, a constant energy. That it does, that should not be surprising because there's mathematical results. No physics needed to get from Lagrangian to energy. So that this works, I'm not surprised. Introducing this other field, again, let's go through the arguments again. Any random field will give you the Schrödinger equation, but that does introduce this new party field. Party fields should agree with nature. If you don't want to introduce a new field, the only thing you can do is make party field already some version of your original field. So you don't introduce anything new. Then we find two equations. One was a Schrödinger equation by construction, because that's what you set out to find. But you also find an equation for psi star, and apparently psi star and your psi do not line up in the way that they should. That the complex conjugate of one is actually the other. So mathematically it's all sound. But this apparently is not allowed to be psi star, because it gives you results that do not line up. Conclusion, your Lagrangian is good as far as you want to get the Schrödinger equation out. Unfortunately, it bites itself in its own tail. But again, this is physics. Guessing Lagrangians. You gave it a good shot, because again, this is what theoretical physicists do. They give it a shot. And they ultimately find that it doesn't work, so they go back to the drawing board, try to find something new. Yep. So, if you ever encounter this in your maybe research life in theoretical physics, you just know now to go back to the drawing board and just start over. Try to find a new Lagrangian. What if I do this? There are some other exercises I would like to go through. Of course, you're going to get them all written out. But what if I give you my Lagrangian? And maybe you can fiddle for yourself if that works. Yeah. And just wait for written solutions. Okay? I actually had to look it up because I made some beautiful notes of that. Forgot what they were. And I don't want to do the reverse engineering here because, as you can tell by my lack of sticking to conventions, I probably end up wrong. So I'm just going to read it out from my own notes. Here's the one that I have. And how did I find this? Again, reverse engineering, lots of it. I ran into the same problem as you, that I had to introduce some other field with respect to which I had to take the derivative. So I also took the complex conjugate field. I had no choice. Otherwise I had to introduce something new, party field. And that means introduce new physics. I started with this term. Maybe you can already see why. Because I know that my original Schrödinger equation should give me something like second derivative with respect to. Do you see that? Now in my Euler-Lagrange equation, if I now take the derivative of my L with respect to spatial derivative, I get this one back. Right? The derivative with respect to this thing gets me that thing. But that gives me one derivative. And the Schrödinger equation tells me there should be two. Fortunately, the second one comes from Euler-Lagrange itself. That gives me my second derivative. This is how I got to that point. Yeah, I mean, this is more an art than a science. Now, that's not all, because the only thing that I get now is the second derivative with respect to space. So I get this one now, so that's good. I, by hand, plug this thing in because our Schrödinger equation has this as its 4 factor. So I put that in too. Also note that I make sure that my psi conjugate field and my psi field are built in exactly the same way. Why would I do that? Speaking of little tricks that tells you what a Lagrangian should look like, why am I building my, every time I write down a term in my Lagrangian, I will write down a couple more in a second. Why every time I introduce a psi field, I make sure that I introduce a psi star field in exactly the same way? Why would I do that?
Because then if you do the thing that didn't work for their solution, it will work out.
Yes. Yes. Because I know that my psi field and my psi star field should fulfill almost the same equation, right? I mean, it differs a minus sign in I somewhere. If I just write down something else on my psi star field, I will end up with the issue that you had, that your my psi star field will obey very different differential equations. I really make sure by hand that they appear in my Lagrangian in the same way.
Why do you have the delta then the I? Could you also just switch it around, right? Or
What do you mean?
you have delta I and then your field.
Yes.
Can you also just switch it around?
Yeah, as in first you did this one and then that one?
Or first the I and then the delta? Or
Isn't that a subscript?
I think the I is like an index.
Oh, it's index I. Oh, I'm so sorry. No, it's index I. Oh, excuse me. No, you're right. No, I should have said that. This is just me being used to notation. The I means derivative with respect to space. X, Y, or Z. Doesn't matter which one. Okay? And there's something else too. This is a summation. So what it says here is derivative with respect to X times derivative with respect to X complex conjugate plus the same thing with respect to Y plus same with respect to Z. So maybe just for completeness, I would just write it out in full. X derivative, same thing for Y derivative. And again, now you see what I
can't
said.
you just
Common factor.
Sorry?
could you also write it as delta mu and then minus delta 0?
Yeah, we could have also done that. That would have been the same thing. That would be a short version. So that's this. This gives me that. Can I erase everything by the way? Yes.
How do you get the, like, why don't we want the time component?
Oh, we do. So we're not there yet.
Like, we want it to pop out, but we don't introduce it.
No. And the reason that I don't introduce a time component here at this point in this form is because the time derivative only comes with one derivative in the Schrödinger equation. So if I write down the time component in exactly the same way as this, I will get a second time derivative and I need only one. So I know that my time derivative works by a different rule.
Yeah.
By the way, for the people who are familiar, I mean, as really have swam in special relativity, the fact that I have to introduce my time derivative in a different way than my space derivative tells me that this equation cannot be relativistic. Because in relativity, special relativity, time and space are treated in exactly the same way except for a minus sign. So the fact that my Schrödinger equation has only one time derivative and two space derivatives means that they're not interchangeable. In other words, that this result cannot be in accord with special relativity. Not surprising, because the Schrödinger equation does come from the classical energy equation. Okay, so this part, let me just write down what the again, I engineered this such that if I now take this derivative with respect to the space components, I will get these guys out, the single derivatives. And then the second derivative that comes from Lagrange gives me exactly the second derivative I need in my Schrödinger equation. This is how I got this form. Just repeating my arguments, and I make sure that my psi and my phi's, this should be called psi's, I guess, right? Let's be consistent. I make sure that my psi's and my psi stars are built in the same way, so my psi and my psi star will follow the same equation. And I don't get the issue that I have two equations that are not each other's complex conjugate anymore. Okay, now we have to build in a time derivative. Again, it's just playing around, and I'm just reading this from my own notes. I did it like this. Oh yeah, there it is. That one? There you go. And, well, let's concentrate on this one first. If you, using phi's instead of psi's, you know what I mean. If I now take the derivative with respect to the time derivative, delta zero of this thing, well, it gives me there you go. If I take the time derivative of this thing with respect to t0, I get this thing back. You see that? Now that is not in the Schrödinger equation. There's no psi's in the Schrödinger equation, just derivatives. But fortunately, this one gives you exactly the time derivative that you need. Right, what I want to get out is this. This one's taken care of by these first three terms, plus v, get to that in a second. And I also want this to come out. Now this will come out because if I take the time derivative, the derivative of this thing with respect to dt psi, I will get this. And then the contraction tells you of that thing, if you take the time derivatives, it gives me exactly that. Now I use my other argument again. That my psi's and my psi stars should be built in exactly the same way, otherwise they will ultimately give me different differential equations. So what should I add to this? At this moment, my Lagrangian treats my psi's and psi stars in a different way.
And on the term with the psi star and psi reverse?
Yes, exactly. But, so something like this, yes? Because now, what I have is that they come back in exactly the same form. Again, plus or minus.
Plus.
Plus.
Probably minus, because there's an I.
It's probably a minus. Again, this is just, you guess what it is, you put it into Schrödinger or Lagrange and see what happens. It's probably a minus, or whatever, maybe this is a minus, that's a plus, but they should have opposite signs. Because the I, complex conjugate, right? So there you go. Okay, so maybe up to a minus sign somewhere, we have now everything with this part, we have that part. Does anyone see why I put the over 2 in there? Because what I should get back is not over 2. See that? These things give me this times 1/2. That's not a coincidence, not a typo, it's not a convention. Not me messing around my physics or my maths. There's a reason. Put put these into this part of the equation, gives me this with a factor 2.
Does that have something to do with the other side of the equation?
Yes. Because I can now take this Lagrangian, this part of Lagrangian, and put it in here. With respect to psi, I get my other ddt. And with that half, and the half that came from this side to get maze 1. Okay, just put it in, you see that it works. Okay, so this part is taken care of, that part is taken care of, not this one. That should be easy. Let's take a guess. I want to put each part of my Lagrangian in such a way that this comes out. So proper reverse engineering should be going on now.
That part was correct in there, no? We got the V out, so we can just use the V multiplied on both sides by the expander.
Thank you. Okay. Take the derivative of this thing with respect to psi, and you get phi psi star. So there we are. So this would be my initial guess for my Schrödinger Lagrangian. And as you could tell, there was some art in there, some guesswork, but it was educated guesswork. I knew what format it sort of had to have. The psi's and psi stars should have the same role in there, up to minus signs maybe with i's. And then I just reverse engineer in such a way that it works. So here we go. So that's nice. And because I put psi and psi star in there in the same manner, that means that if I do this Euler-Lagrange equation with the psi's, I get an equation for psi star. If I do this Euler-Lagrange with psi star, I get an equation for psi. Those two should now give the same answer. Should now be each other's complex conjugate by construction. Should we, for funsies, see if it actually gives us a Schrödinger equation and its complex conjugate to see that it actually works? So let's first do it. So this is my guess. Maybe some minus signs wrong, maybe some plus signs wrong. We will reverse engineer those back in a moment. Okay, let's find the differential equation for psi. Well, in order to get my psi's out, I have to take derivatives with respect to psi star. My Lagrangian. Help me out. What will come out? Go through term by term. What's the derivative of this thing with respect to psi star?
Zero.
I would say 0. There's no psi's in there. There's only derivatives of psi.
Oh, yeah.
Alright, so let's be explicit. This part is 0. The same argument, 0, 0. Okay, this one. Time derivative, excuse me, psi star derivative of that thing. What does it give us?
I h bar over 2, the derivative of time.
Yes, thank you.
Psi.
Thank you. Alright, so there's that. Oh,
Yeah. The last one.
exactly. So it gives us this.
Mm-hmm.
Okay, oh, that's good. Nice. Alright, this one taken care of. Let's do the right hand side. It's always the one that takes the longest. And as you know, this is contraction. So you should read this as psi 0, dl d psi 0 psi star. I'm writing it out in full because again, this is I as in x, y, z. Very confusing because there's also a complex I floating around, but as an index I mean x, I, z. Let's do this one first. Time derivative. There's a, yeah, oh wait, one of these, yes?
Yeah.
So which one is it? It's this one.
Mm-hmm.
Okay, so that gives us minus I h bar to psi. Yeah? And then the derivative of that one with respect to time uses minus 2. Alright, so this one is taken care of now. Let's continue.
Now with respect to space, yeah?
Yes.
Double derivative of all the spatial components. Sorry.
So something like this. Not sure what you said, Sophie, but I think it was this derivative, yes? So this one. I think that's it.
Mm-hmm.
That's it? Yeah, I think that's it. Alright, then Euler-Lagrange tells me left hand side should equal right hand side. In other words, I h bar 2 dt psi plus v psi should equal minus h bar over 2. It's surprising that when I do deduct physics, I constantly leave my h bars out. When I should do Schrödinger physics, I can't help but put them in. It's just really, there's that. Is this a Schrödinger equation? It sort of looks like it. I mean, what I have here is minus h bar over 2m. This is a contraction of psi I with itself, yes? So that's the second derivatives of all space components. In other words, this one of psi, that's this, minus v psi, that's that one. Go to the other side, get all time components over the other side. Minus I2 dt. And this one brings in another one, gives us I h bar dt psi. Is that the Schrödinger equation?
Potential should be positive.
Yes. This should have been positive. So there was something wrong with our Lagrange, one that's easily fixed.
Minus.
Exactly. Apparently this had to be minus. This is reverse engineering, yes? I'm not smuggling. It is reverse engineering. Okay, so we have a Lagrangian now that indeed gives us a Schrödinger equation. So far we have the same thing as 7e and chi. But let's see if we also get the psi star Schrödinger equation out, and that these two don't contradict each other. So we're going to do the exact same exercise. That means that we have to take derivative with respect to psi 0 to psi itself now. Now we can go through the whole derivation again, or we can just make proper adjustments here. Maybe for completeness it is nice to just go through this again. Of course there's a faster way, but you know what. There you go. Psi L d psi. Let me correct the minuses, by the way, that we did wrong along the way. This is correct. There you go. Alright. So what should we have now? Di L dl d psi?
It's the V component.
Which one?
Just the, psi star V.
Yes.
Negative psi.
Yeah, exactly, because we saw that it had to be corrected, so that's... Alright, but that's not all. There's another term in the Lagrangian that has psi's.
The negative I h bar over 2.
Yes.
Time derivative of the psi.
Yes, there you go. Psi star. There we go. That's it, yes? Alright, left hand side taken care of. Right hand side. Again, I'm going to write it out in its separate terms, time derivatives, space derivatives. Again, for people to know, this is how you can tell this is not a relativistically invariant physics that we're writing down, because time and space obey their own separate rules here, apparently. But that's fine. Who cares about relativity anyway? There you go. Well, I do on Monday, 4 o'clock. Everybody set their alarms. Now let's go through this a little bit fast, because take the time derivative of Lagrange with respect to the time derivative of psi. that is this one here. And I have to take another time derivative of that thing. So all in all, what you get is I over 2 psi.
Yeah, first
Yeah.
derivative.
Thank you. And then psi star, yes? Okay, good. So there's that. And what else? Spatial derivatives. This thing, space derivatives, there's 3 of them. I'm going to write them all down in one go. Minus h bar squared 2m di squared psi star. I think that's it. Went through it a little bit faster than in the previous case. Same mathematics. Euler-Lagrange tells you that these 2 terms should be equal to each other. Left hand side is right hand side. So that would give us minus psi star v minus h I dt. This one, other side equal to question. This is what we get from our Lagrangian. Is that indeed the Schrödinger equation for the complex field, for the complex conjugate field? Yeah. That wasn't guessed. You actually saw it, of course. I'm looking at you as if you said it. Was you? I heard a female say yes. That was you. Okay. It wasn't a guess, though.
I never wrote down.
Well, let's write all Schrödinger. I just write down the same equation, but in its usual form. I get this one. Then I get this one equals I made a mistake. This should be honest.
Yeah.
There you go. Is that indeed the Schrödinger equation?
Where's this factor of 2?
Those 2 have cancelled by construction. Yes. Is that the Schrödinger equation?
Yes.
But wait a minute, there's a minus sign here. The original Schrödinger equation did not have a minus sign. And the time derivatives.
Conjugate.
That's because of complex conjugate. You take this thing, the whole equation, complex conjugate, you get exactly this one. In other words, they agree with each other. And now what we have is a Lagrangian that indeed has psi and its complex conjugate, gives you 2 equations, and these 2 equations agree with each other. That was the one thing that previous speakers did not have. They also had a psi and a psi star. Okay, but they gave them 2 equations, but these 2 did not line up. So this is how they could tell that their Lagrangian needed some fixing. Again, more an art than a science, but here we are. Now I will leave the rest up to you, that if you now have the correct Lagrangian that we've now explicitly checked, put it into Euler-Lagrange equation, check what the energy is. And I promise you it will give you the energy that in quantum mechanics, Ronald and such, he always put in there. He always said, well, there's the energy here, there's an E. Put this Lagrangian in there, you'll get that E back. So that's nice. What I'm saying here is Ronald and I agree on physics. Break time maybe? Yeah? Which means coffee time.
Yes, I always say that now.
There's 2 things we forgot just a second ago. One of them is an applause for the 3 people who did the And the second thing, Chai made a nice comment before the lecture started. He came to my office, and I'm just going to mention it and do with it what you want. He made a very good comment. Namely, we have a Schrödinger equation, we reverse engineer the Lagrangian, and then we put it back into Newton's theorem to get the energy. He came around and he said, but wait a minute, isn't the Schrödinger equation already the energy? Right? I mean, we got it from the energy expression, and he's right. Period. Yeah. So you might think, oh, so we got an energy out while we started with an energy, so isn't that sort of what's going on there? Oh, that's true. Comment that I would like to make there is this thing and then getting an energy out is a mathematical exercise. Yes, it doesn't care whether the thing you put in there was already an energy. So physics-wise, you might say, well, we really just rewrote everything in terms of Lagrangians and didn't get anything new out, and that's true. From mathematics point of view, it is a good exercise. Just to see how that works, how you get all that stuff out. So there's that. No more comment there. Okay. I want to go through some of the other exercises. Now there are some that I picked that I think are important. Well, all of them are important. As I wrote you, my original set of exercises were, well, emphasizing some other points of the physics. But after Tuesday's lecture, I decided to rewrite them a little bit, just so that going through these exercises now really is just a big recap of the lecture, so you can see everything in full detail. And I took the liberty of now putting in the right minus signs everywhere, sticking to dimensions and such. There might still be missing minus signs somewhere. Well, we'll see as we go through them. So, if you had difficulty getting through the exercise or getting through the lecture, understand what was going on there, and/or you find these books not to answer your questions, then going through the exercises will get you through the whole lecture. It completely covers everything that we've done. Now, here's one exercise. It was about Lagrangians. Let's do a classical Lagrangian. Now, the classical Lagrangian is a function of x and v. There you go. And the classical Euler-Lagrange equation looks like this. So, people are really into puristic calculus know the difference between the curly brackets and the straight brackets. If you're not into that sort of stuff, don't worry too much about it. There's a difference. Don't worry too much about it. Okay. One question that I ask is, now suppose that you have a Lagrangian and it gives you a solution. Here's a Lagrangian. This is a Lagrangian that actually gives you classical mechanics. Just reverse engineered. I reverse engineered this thing in such a way that if you now put it into Euler-Lagrange equation, it just gets Newton's second law back. This is not proving Newton's second law from first principles, it's just rewrapping the stuff they already knew into Lagrangians. Okay. Now, question that I have now is supposing you take this Lagrangian and you multiply by any number. 15. Two questions. Does that change your laws of physics? That's question one. Question two, does it change the expression for the energy? Let me write down energy again. Or Hamiltonian, if you will. You take a Lagrangian and you know that it works perfectly fine. You multiply it by 15. What changes in your laws of physics? What nature does? Principle of minimal action. What changes about the energies? You can immediately tell this by mathematics.
Everything just gets 15 times bigger.
Yeah. Everything being, well, there's a 15 here now. There's a 15 over there. Doesn't matter. Mathematics just drops out, yes?
Yeah.
The 15 is a number, so it just goes right through the derivatives. So you just end up with a 15 on both sides, you just cross it out. So apparently Lagrangian multiplied by any number just gives you exactly the same physics. So this stays exactly the same if L is replaced by some number times L. Here's an interesting question. How about the energy? It changes, because now this carries an extra 15, this carries an extra 15, your whole energy will carry an extra 15. So this, the energy will become 15 times bigger, 8 times bigger. Conclusion. For any Lagrangian, there's an infinite amount of other Lagrangians that gives you the same physics back. Just multiply by any number. The energy will change accordingly. That is not an issue. Because notice here, this expression just guarantees that whatever number comes out, that is constant. Doesn't tell you what the number is. In fact, if you multiply by minus 15, this stays the same. The energy becomes a negative number. Is that an issue? It's an open question. Okay, apparently the mathematics doesn't care about putting a minus sign in front of everything. But the physics all of a sudden tells you there's a negative energy.
Negative Lagrangian as well, right? So that doesn't really matter.
No, you're right, you get a negative Lagrangian, that's true. Right? I mean, if A is minus 1, then again we see that this will stay the same. You get exactly the same laws of physics back. But your Hamiltonian, or your energy, if you will, becomes minus Hamiltonian. So energy all of a sudden gets a minus sign. Is that an issue? That is my question.
Well, because your laws are also minus.
No, your laws are minus. The minus that you put here, the minus that you put there cancel each other out.
That doesn't work.
So it is an issue?
Sorry?
So it is an issue?
That's my question.
I guess so. That was the whole problem in the beginning. Like when we were talking about the other formulas that they would use over the negative.
Klein-Gordon and Dirac.
Yeah.
Now, I propose to you that it's not an issue, and that there's a difference between this situation and the Klein-Gordon and Dirac situations. But I can imagine that you have to really, well, it's a subtlety somewhere. And I wondered if somebody might know what it is. Yes?
Didn't you put a formula on the board? I think it was to do with Mitchell's theorem, where you took the modulus square of the thing anyway, so the energies.
Oh yeah, no, that was the solution to the Klein-Gordon equation. The energy though, wait a minute, maybe we're not talking about the same thing. When I wrote down the expression for the energy of the Klein-Gordon one, it turned out to be something, I forget what it was, I think it was something like this.
Yeah.
And then I would say, oh look, so it's all positive, no issue there. Was that what you were referring to? Okay, now what we see now here is that if I take my Klein-Gordon Lagrangian, and I would have given it an extra minus sign, it would become a negative energy. Problem? Question mark? Answer is no. Yes, sir.
Couldn't you state we just do the lowest state? So you have like minus 15 up with H, and that's your lowest, your ground state.
Yes.
You can set it as a ground state.
Yeah.
Sort of parsing what you're saying, but I'm not quite there yet. You say something, okay, now you have a ground state?
So basically, suppose that you find an energy without a minus 15 factor.
Yes.
You find an H0, and then you times minus 15 inside. You have negative H0, but you can set negative H0 and negative 15 H0 as your ground state.
Yes, but the other states are going to be lower than that now.
I see.
Because all the energies now get an extra minus sign.
And just, like, couldn't the negative sign just tell you the direction of the energy? Like classically, if it's going in or out of the system. So
I know what you mean, but now you're talking about not H or U, internal energy, but du,
yeah,
the direction of the
du.
flow. But this is the energy itself. Arslan.
I was thinking that energy itself is an abstract concept, and it depends on the sign of Vx. So if you multiply it by minus 15 and Vx picks up a positive sign, then and you define your energy relative to the potential that you're working with.
The only exactly. No, you're saying what I was going for. There's a subtlety involved with the Klein-Gordon and Dirac, because there I made the whole point out of negative energies and that was no problem. Now all of a sudden I say that it's not a problem here. First of all, let me first address your point. The negativity of the energies is not so much an issue. The only thing you care about is energy differences. Energy difference will still be the same, even if both the states that you're comparing each other with have an extra minus sign, right? You would still have a same delta E in between. And physics is only encapsulated in delta E's, not the E's themselves. This is why the first law of thermodynamics is written as a du. It doesn't say anything about use, it tells you about energy flow. So in that sense, it's not an issue. So putting a minus sign in front of your energy really doesn't change anything, as long as your delta E stay the same numbers. Okay, so that's one. Now, why did I make a point out of Dirac and Klein-Gordon having negative and positive? Because in Klein-Gordon and Dirac you had multiple solutions. And you found that if one of them was positive, then necessarily the other one is negative. And then you do run into an issue, because you have now two sets of solutions. One of them is not bounded from below, the other one is not bounded from up. So one of them will run away. Is that an argument you can follow? That is a subtlety here. Over here, you in classical mechanics say you have only one solution for energy, right? Forget about the minus signs, it's only differences in energy. But in Dirac and Klein-Gordon, we have multiple solutions, one of them plus and one of them minus. It's okay to have one of them to be minus. You cannot have both minus and pluses. So this is why it's not an issue. Alright, let's move on. The other question that I asked now is, suppose you take a Lagrangian, forget about the 15 times 15, do plus 15. Do the laws of physics change?
Just get checked.
Yes. I mean, it's just a constant, and in your Lagrange, with respect to that constant, plus 15 is going to give 0 on both sides. So this law will be exactly the same still. So this stays the same if L is multiplied by a number, and or L gets a number added, whatever the number is. How about the energy? Does the energy change if you add constants, subtract constants to your Lagrangian? So by looking at the mathematics. Does this part change if you added the constant to L? This one didn't. How about this one?
Yeah.
That changed. Alright? So apparently your energy, Hamiltonian, gets replaced by minus A, minus because of minus L over there. So you've shifted your energy levels. Is that a problem, physics-wise? And indeed, the answer is no. Because you're only interested in energy differences. If you shift all levels by a certain number, the energy difference will stay the same. So physics-wise, this happens if you multiply, this happens if you add. Or mathematics-wise, that's what happens. Physics-wise, no change in actual calculations. The numbers come out different. The laws come out the same. So there's that. Conclusion, grand conclusion of this whole exercise too is Lagrangians are not unique. For every Lagrangian that you found, you can build 1,000,000 times other ones, and all of them give the same physics. Different numbers maybe for your energy, but same physics. Lagrangians are degenerate. That's a good thing, because if you're in the business of guessing Lagrangians, you don't have to worry about that one that you have to find. There's a whole plethora you can find, and they all work. So that's good. These are not the only ones, by the way. You can also do other stuff with Lagrangians in such a way that this one doesn't change. And I might make it an exercise, exam-wise.
Just repeat that one.
Yeah, okay. This is the moment that people think, wait a minute, I should pay attention now. Okay. What I'm saying is, these are not the only things you can do to Lagrangian to get the same laws of physics back. You can also do less trivial things to the Lagrangian. And the less trivial things, so actually add something that is not just a constant or multiplied by a constant, but an actual function itself. Eagerly writing all of a sudden, everybody. That you can actually add something to this. Some non-trivial thing, and still they're saying it's the same. That's a calculus exercise. What can you add to L in such a way that if you take this combination derivatives, everything drops out again? And you might actually find it not in this book, but it's probably in that one. Anyway, so everybody go and PDF that one. It's in there. I think it's chapter 3.
That's right.
That's Ryder. Yes, the yellow one. But they do it in full quantum field theory using group theory, so it's in there in some obscure way. Don't worry, if I make an exercise, I'm actually going to give you what the thing is, and then ask you to just put it in there and see if it actually comes out. I'm not promising that this is an exercise though, but it's something similar. Okay, again, conclusion is yes, you can actually have multiple Lagrangians and not just the trivial rewritings of the Lagrangian. Alright, so there's that. Now, in the minutes that we have left, there was one exercise that I found extremely enlightening, and I want to show that to you. Namely, at some point it asks you to derive the energy of the Dirac field. What I promised in class was that just as in the Klein-Gordon case, you will always find a positive energy. It's a real number, it's a number, period. It's a real number and it's positive. Klein-Gordon, we saw that was the case. Regardless of if you put in the negative energy stays with positive, it's always positive. Does the same thing happen with Dirac? That's the question. Can someone remind me, this is not a trick question, I actually don't remember it that well, what the Dirac Lagrangian is. So we're going to prove that the Dirac solutions are indeed always positive and real, because energies need to be real. Nobody needs complex energies. Thank you. I actually know it. It was a trick question. Just to be sure. There we go. I did it on the train yesterday again, so it should be somewhere in my short-term memory at least. I think this is it. I don't recall. Did we actually put this into the Dirac equation? Yeah, we did. We
didn't lecture. It was a convention thing again, so we ended up putting a minus, but maybe we changed that again. I don't know.
We changed it again.
Okay, good.
This is the correct one.
We changed it twice, right? Okay,
yes.
Yeah, okay, good. Sure.
Yes. The one that I put on the exercises, I rewrote the exercises that afternoon. That is the correct one. And you can actually prove that for yourself. Unless you go to quantum field theory by Rider, where you use the opposite convention. Yeah, authors. Gerard de Hooft, the Nobel Prize winner, he makes a point out of it. If you ever follow lectures with him, he switches conventions all the time. Not the mid-calculation as I do, as the stupid mistakes. He actually does this, okay, we have this one calculation, I'm going to start this new calculation, I'm going to use the opposite convention now. And when students complain, he always says, hey, listen, if you can't keep track of minus signs in mid-calculations, you're not a physicist. So, or it's just another way of saying, I should be allowed to have minus signs anywhere and just change it. I might actually cut that out of the recording. Okay, so here it is. Yeah, we actually showed that this actually gives you the Dirac equation. What we did not show you, we did not do, is again we have two fields now. We have the spinor, and we have this other spinor thing. That is just a shorthand notation for that one. And just as we did with Schrödinger just now, that means that we can do Euler-Lagrange two times, one for this field and one for that field, and they should line up. They should give you, they should contradict each other. That itself is an exercise. But, as books would probably say, I will leave this as an exercise for the reader. But that is the case. Now, let's go to the energy. Energy, or Hamiltonian if you will, is for quantum fields given by this number integrated over all space. And I think in the tutorial a couple of days ago we actually already wrote at least down what the final expression was, yes? And I think if memory serves it was, I have no idea actually, something like this.
Nobody tell him. Yeah.
I think it was, yeah, otherwise we're just going to put, you know what, I'm just going to plug it in, why not?
Minus L.
Yeah, minus L. So it should be plus this or something.
Yeah.
Okay, there's that. Not sure yet. Oh, right, just do it right here, right now. Derivative with respect to psi dot. Psi dot is in here, gives you gamma 0. That's this one. Multiplied by psi dot itself. That's that one. This term is correct. Should be an I. You're missing an I. Okay, there we go. So that sucks, we have a complex energy now, or do we? So there we go. This thing, we have to subtract the whole Lagrangian again. Let's do some proper subtracting. Minus I, psi bar, the full gammas, plus m d3x. There's this. Well, what I do see happening is that the psi zeros here cancel each other out, right? Because this contraction also contains a psi zero. Yeah. Psi zero, you know, derivative with this psi with respect to time, such and such, blah blah. That gives us minus I psi, and note my notation again. This I is an index I, it means contraction over spatial, x, y, z. Three questions. First of all, is it a number? Is it real? And is it positive? Now, I hope from this previous exercise you understand that it being positive is not so much an issue. Right? If it's negative, energy differences will still be the same, you still have the same physics. Or, if you don't like this thing being negative, just multiply the whole Lagrange by a minus sign, not out of convention, because it gives you the same Dirac equation anyway, physics doesn't change. So any minus signs in your, overall minus signs in your energy is not an issue. You don't like those, multiply them, everything by minus 1. That's the point of the whole exercise too. But here's the thing, we have 4 solutions for the Dirac equation. I don't care about one of them having I don't care about getting an energy out that is negative per se. What I do care about is some of these solutions giving a negative energy and some of them are positive. That is the issue. Not so much that one of them is negative, that they have opposite signs. So what we should do here, is to check whether this is a positive or a negative number, we have the 4 solutions. We wrote them down before. In fact, one of the exercises of the previous tutorial, a week ago, was to actually prove that these are solutions. They are solutions. Yeah. So all of this boils down to take those 4 solutions, plug them in here, and check whether they all have the same sign for this whole expression. I promise you that they do. Again, 3-hour train ride, had a lot of fun doing exactly that. Now this is an exercise in algebra. Now without actually plugging the numbers in, let's just check if these are positive numbers and if they're real. First of all, are they numbers? I mean, we're putting in spinors. And a spinor is this vector thingy.
Well, every time you're having like a side diagram.
Yes.
Side, so they're
yes.
numbers.
Okay, good. By the way, this is called a joint spinor, the bar thingy. So Hermitian conjugate of the spinor times gamma 0 is called a joint spinor. Just nomenclature. Yes, you're right. Let's go through this this is a spinor itself again. Right? This is 4 thingies in one column. Because psi is, so the derivative is as well. Multiplied by a matrix, 4 by 4. Now a vector multiplied by a matrix just gives you a vector again. So this whole thing is again a 4 by 4 thingy. This thing, you're right, is the, what do I call these things? The latent parts or something?
Row vector.
Row, thank you. Yeah, a row vector, exactly. It's a row vector. A row vector times a column vector is a number. So it's a number. This part is a number. Same argument applies here. So whatever comes out, it's a number, it's not a spinor. That's good because we want energies to be numbers. That's nice. We should all thank Emmy Noether for this again. Can you just make one more comment about Emmy Noether? The poor lady, where everyone would have quit their jobs, or would have done something else that actually got them recognition, she stayed. Well, what test of character is that you actually do that for 5 years? And have other people parade around with your results because you had to put their names on them because you couldn't publish them. And she still stuck around. I think it is cool. And she was pretty too.
Well, that's what
Marie
we're
Curie.
No, that's not what I said. No. That's not what I said. It's a bonus feature, okay?
Bonus one.
Unlike Marie Curie, who look
Beautiful.
scary.
Yes. A goddess walking on water.
Yes.
Thank
We
you.
won 2 Nobel Prizes for chemistry and for physics.
The Beyonce of science.
But if you see her picture in the Solvay conference, she actually looks like she's going to come out in Mercury.
What a boss. Yeah. Like goals.
But then again, let's be consistent. If you look at the Solvay conference, right, the picture from 1927 or so, you look at the picture, you look at the guys, those are not much to look at either, okay? Let's see, yeah. Is it a real number? That's a little bit more hard to tell. This part you can already tell this has to be real, because it contains a complex conjugate. And of course it's all wrapped up in more difficult stuff, but again, the adjoint is psi thingy. This by itself is transpose complex conjugate. So whatever spinor is, you multiply by its complex conjugate. And any number it's a spinor, but any object that you multiply by its complex conjugate will give you a real number. So it is real. It is positive too. It's modulo squared and such. So this is real and positive. Again, this part is just really a matter of taking your 4 solutions, plugging them in, and doing this full matrix equation. Again, this is a contraction. These are 3 terms. 3 matrices, x, y, z, gamma x, y, gamma z, gamma y. And 3 subscripts. Calculate all 3 of them, add them together. That's what this says. I will guarantee you, give you a real number. I have no quick way of showing this to you. Some people might find it not the most beautiful way of looking at it. It would be nice if you could just tell immediately, like in the case of the Klein-Gordon, could tell immediately that is a positive number or a real number and such. Here I actually have to take the explicit expressions for the solutions. It's not the nicest way, according to some people, but it does work, because we know there is only 4 solutions. And so if it works for all 4 of them, it works for all of them. No extra work to be done. This is algebra, doing the math. Ran out of time. Now, there was one more exercise, and that was the big one, and that is do this whole finding of the, I'll be with you in a second, but do the whole exercise of the AMU field and show what it does. If you put it in the Euler-Lagrange, what you will get is exactly what I did in the lecture a couple of days ago, but corrected for minus signs and such. If you go through that, you will find exactly the solutions that we ended up with last time. I will write them out in explicit detail, and of course you will see them in the written solutions as well. That ultimately, if you make this, well, not this one, or you can also do it with this one, but if you make the Klein-Gordon version locally gauge invariant, that meant that you made it in such a way that you could replace your psi or your Klein-Gordon field by the same thing times a complex phase. Do you remember how to do that, by the way? It was a very easy trick.
Replacing delta mu by big D.
That's all you have to do. I showed this, that it works for Klein-Gordon, and just by trying it out at Dirac, you'll see that it works there too. Now, what is big derivative? Called covariant derivative. It's small derivative, plus or minus depending on convention and such. That thing. If you do this, and you plug it into there or Klein-Gordon, you get one that is actually invariant under giving your fields a complex phase. What you do have to do is assume that your A field, whatever it is, itself goes like this. And lambda being here the complex phase. Do this, put it in there, you can check that it works. Again, it's an exercise in algebra. Here's the solutions that you get, because just like in your presentation before, if you introduce another field, you get new physics. We had to introduce new fields because the only way to make this locally gauge invariant is by using this trick. So that means we have a new field with its own new solutions. And if you go through the exercise, then again, corrected for some minus signs and such, you would get this out. Just Euler-Lagrange. Oh, you had a question in a second ago.
You can complete
Thank you.
that.
Okay. It's just the final sentences. If you take this one, or the Klein-Gordon one we did, put it into Euler-Lagrange, and you look for the Euler-Lagrange equation for the field A, this new field, this is the equation that you found. This is what nature does when it comes to the A field. Again, it's by mathematical necessity that it has to exist, so we have to take it seriously. Whereas curly J, and I'm blanking a little bit again on the conventions, but up to some numbers, it really is there was that thing, maybe with an I somewhere. There was an I somewhere, I think it was here or something. Yeah. And maybe a factor 2 or something like that. And what we did last time, if you go to the exercise, you see it, that these are 4 equations. For after lambda, there's 1. Lambda 0 gave you this equation. Remember this? There was that. Gives you the first Maxwell equation. And it tells you exactly how to interpret either your Klein-Gordon field or your Dirac field. It's that thing, if you put it in here and you take the 0, it's a measure of how much charge there is. You take the complex conjugate, this I becomes a minus I, gives you the opposite charge. So your field is a charge, measurement of charge, not probability of charge. Complex conjugate, negative charge. If you took the lambda is I as a spatial, and you go through the exercise, you will find that you'll find this equation, that the rotation of this one thing that we call the B field is given by this thing, but now it's spatial components, right? The x, y, z components, times q, plus the time derivative of this thing. This is the 4th Maxwell equation. That you can make a magnetic field either by shaking your electric field or by having a current. Because in Maxwell's equations, this part is a current. How many amperes is going through your wire? Again, that gives you an interpretation of what this field is. Apparently, if you take the 0 part, it gives you the actual amount of coulombs. Well, and if you take the XYZ part of this, it gives you how much the coulombs are flowing through space. Again, if you take the complex conjugate of this gets an extra minus sign, you have particles floating the other way. Negative particles. So that was really the whole message of the lecture. You get the electromagnetic field out, including all the right thingies. We have seen now that all of them have positive energies, even if they flow the other way. The antiparticles, they still have positive energy. Final comment, we now know exactly how to interpret the solutions. They're not probability densities, they're charge densities to tell you how much charge there is at a certain position. One more. Remember this exercise that we already derived this 1 week ago, this expression. That we made a Bohr vector. And then somebody asked me, okay, if not, and then I said this cannot be a probability because it can become negative. Remember that? It was exactly that expression. Without doing this, no Euler-Lagrange. That was just me wanting to make a Bohr vector out of something. And then somebody asked, I forget who it was, but somebody asked me, okay, it's not a probability because it can become negative, what does it mean? Then I already sort of told you it's going to be the charge. Now you see why. So there you go. There's the full of quantum electrodynamics on the board right now. Take this thing, replace your D's by big D's. You have the Maxwell equations, including everything what it means. So there's that. Okay. If you go through exercise 4 of the exercise sheet, I will lead you exactly through all these steps. Okay, I have much more to tell, but it's 5 past now. So, Arslan, you have a question?
That's okay, you answered it.
Okay, good. Okay, we're going to see each other on Monday, if memory serves, yes. We're going to talk about the midterm, going to go through the exercises. If need be, people find these exercises difficult to work through mathematically, even if you know the physics, we can very easily arrange another moment that we can sit with each other and go through these again. Not compulsory, just if you're interested, I'm open to an invitation to sit again and actually do other mathematical steps in case you cannot solve them yourselves.
On Monday.
Maybe. I'm open to everything.
All the solutions online?
Yes, I'm also going to post them online. It's probably going to be over this weekend. And now I'm going to go to the Aperture people. Because I want to set up lectures. Yeah, and thanks for your suggestions. This week might not be the best idea.
Yeah. This coming on.
Maybe okay, next week better?
Or maybe